Alright, we're on section 10.3, writing ionic formulas. Here's our objectives: be able to provide the correct formulas for binary ionic compounds and ones that contain metals with variable oxidation numbers. Alright, so let's take a look at this compound, which is supposed to represent sodium chloride, NaCl. And notice that, if you look at this, it's really hard to figure out which ones go with which. We talked about that in the last video. So what we do is we write what's known as an empirical formula, the lowest whole number ratio that we can write. So in this example, there is every one of these purples, there's a green that goes with it. So there's one sodium and one chlorine. So that's our lowest whole number ratio. That's known as the empirical formula for sodium chloride. So we don't refer to these as molecules, and that would be incorrect to call them molecules. What they are is formula units. They are known as formula units. And most of the solids that you see, like in our chemistry room and stuff, most of these are ionic compounds. Those are the solids tend to be the ionic ones. If you see liquids and gases, those tend to be more of the, later on we'll talk about covalent compounds. So a formula unit is the empirical formula for that ionic compound, in this case NaCl. In order to predict some formulas, you need to know some basic things. And some of these are really easy, and I would even suggest that you write some of this stuff down on your periodic table if you want to. But in group 1, all of them always have a +1 charge. That's pretty easy. Group 2, +2 charge. Group 3, +3 charge. So those are kind of your typical main ones in the group A that are the metals that tend to form the cations. Group 6A, they tend to form -2 charges. Group 7A, -1 charges. Those are kind of our main ones for the main groups, the representative elements that form ionic compounds. Notice that we haven't always talked about group 4 and 5, and certainly we haven't talked about group 8. They don't form anything. 4 and 5 tend to form more of the covalent compounds, which we'll get into in the next chapter. There are a few exceptions to that, but in general, that's what they do. There are obviously a lot of metals that are transition metals, and these are a little bit harder because they don't always form just one ion. They can form two. So for instance, you can have copper with a +1 or copper with a +2 charge. And you just kind of have to learn some rules, how to figure out which ones of these are going to be, and there's a naming convention that we'll use that will indicate which of these that we're talking about. Of those transition metals, there are a few, so we said that a lot of them have multiple ones. These three, silver, zinc, cadmium, they only have one, so it's good to kind of memorize those. Say, okay, well, silver, if I'm talking about silver, it's always silver +1. If I'm talking about zinc, it's always +2, cadmium always +2. When we're talking about binary means two different elements. It doesn't necessarily mean only two elements. In other words, the formula MgCl2 is a binary compound. There is two different elements, magnesium and chlorine. An example of what's not a binary compound would be something like try that again. Okay. MgSO4. This would not be a binary compound because it has three elements in it. So this one's not, this one is. When we do binary compounds, we always write the cation first. Star that. Because if you put them backwards, it's going to be wrong. In other words, we do write it NaCl because Na is our plus and Cl is our minus, and we write them cation first. If you write ClNa, despite it being the right ratio, that's going to be wrong. Cations are always written first. So in this formula, Na2O, it means we would have 2 sodium atoms and only 1 oxygen. And ones we don't write, just like in algebra, you don't write 1x, you don't write the 1, you just write it as x, and so on. So the 1 is assumed if it's not there. if we're talking about an ionic compound, this term, this oxidation number, is a term you're going to hear quite a bit from now on. Oxidation number is equal to the charge when we're talking about ions. So if we're saying sodium has a +1 charge, its oxidation number is +1. If we're saying magnesium has a +2 charge, its oxidation number is 2+. So let's work on writing some formulas. I'm going to go through kind of a slower way to start with, and eventually I'll show you a little bit faster way here to do this. But let's say, first of all, if we look up aluminum, and we know it's in group 3, we know it has 3 valence electrons. So it looks like that. And let's say it meets a chlorine. And we're trying to figure out, well, what's going to be our formula here for this? Well, chlorine, we know, it's in group 7. It has 7 valence electrons. So remember, chlorine has an empty space, and it says, hey, I need one of these. So it's going to steal that one. Now, the chlorine, this guy's happy over here, but the aluminum still got 2 extra ones. He's not happy, so he needs to meet another chlorine. So now we've got another guy here. Oh. And he says, hey, I'll steal this electron. And that chlorine's happy, but once again, this aluminum still isn't happy, so there needs to be another chlorine. So let's put this like this. And he's going to steal this one. So in other words, this aluminum had 3 valence electrons it wants to get rid of. It has that, doesn't want to hang on to them, doesn't want to gain any more, so it's trying to get rid of these electrons. Chlorine comes around, hey, I want 1. I don't want 3, I want 1. So 3 chlorine atoms take 3 electrons. And now our formula for this would be AlCl3. Now, we can also think of it like this. If we know, hey, aluminum 3 plus, chlorine 1 minus, right? We know that from our looking at our charges that we put. And you could say, well, okay, I need to balance my positives and negatives. Well, how many chlorines is it going to take to balance that? It's going to, 3 plus, here's 1, 2, 3 minus. So I get 3 in my formula. So AlCl3. All right, let's take a look at this one. This one's a little more, complicated. We've got aluminum, which is once again has 3. And we've got sulfur, which has 6. So sulfur says, hey, I want 2 of those. I'll take this one and this one. And now the sulfur's happy, but the aluminum still isn't happy. So the aluminum says, well, I need another sulfur. So find another sulfur. And this sulfur takes 1 of those. But now this aluminum's happy, but this sulfur isn't. He says, I need another aluminum. Okay, so now we find another aluminum. He takes this one. So now we've got 1 aluminum happy, 2 sulfurs happy, but this last aluminum, he's still not happy. So he says, I need to find another sulfur. Okay, so he does that. Goes here, goes here. So when we're all said and done, we've had 2 aluminums and 3 sulfurs. Now another way to look at this is like this. We've got aluminum, which is a 3 plus, sulfur, which is a 2 minus. And you look at, you should be able to look at their aluminum's in group 3, sulfur's in group 2, or group 6, so it's a 2 minus. And then, what I think of is, what's the least common multiple between 3 and 2? Well, that's 6. And so somehow I need to get to 6. So that means I need 2 aluminums, because that gives me a positive 6. And I need 3 sulfurs, because that gives me a negative 6. And so once again, I still get the same ratio. Either way of these is good to think about. I get Al2S3 for my formula. All right, now, there is a simpler way to do this, but it's simpler, but it will give you wrong answers if you don't pay attention. So, for instance, let's take a look at aluminum. So let's write it out. What's our charge? 3 plus. Oxygen. Oops, in group 6, it's a 2 minus. This is known as the crisscross method. And really what this does is gives us a multiple of the 2 numbers here. The problem is it doesn't always give us the least common multiple. So sometimes you run into a problem with that. But all I need to do is cross the numbers. So I would get Al2O3, which is, very similar to what we had for Al2S3. Same kind of thing. So this is a crisscross method, and it works really slick for a lot of things. But you have to be careful if these two are the same value, like one's a 2 plus, one's a 2 minus, or if they're multiples, like if one's a 2 plus and one's a 4 minus or something like that, then you can run into some problems. And you always have to reduce. Remember, this is the empirical formula, which means it's always the lowest whole number ratio. So if we'd come out with Al4O6, while that ratio works, that's wrong. Okay, let's do another one. Let's say we have Mg, which is a 2 plus, chlorine, which is a 1 minus. So we do our little crisscross method. Okay. This means a 1. This is an implied 1, and we don't need to write the 1 anyway. And Cl would be 2. So there's my formula, MgCl2. NaBr, Na plus, Br minus. Cross them. Once again, both are 1s, and we don't write 1s, so we would just write NaBr. Now, here's kind of an interesting problem here. You've got lead and oxygen, and lead, and I don't think I indicated here, but let's assume it's lead 4. Lead 4 plus, oxygen 2 minus. This is where we run into a little problem with the crisscross method if you don't pay attention. Okay, we could just say, hey, let's switch, and you'd get Pb2O4, but that's wrong because we don't want multiples. In other words, you can take a 2 out of everything in there, so we don't want that. So instead, when this is one where the crisscross method, you could start this way and say, okay, I got to reduce it down, but it's actually better to just think about, all right, if I got a 4 plus and I've got a 2 minus, I need 2 of those, so it's going to be PbO2. Now, lead is one of those that could be, multiple things. So, and I didn't tell it here, which I should have, but let's say that it had been a Pb2 plus, which is another possibility of an oxidation number for lead, and O2 minus. Once again, you wouldn't want to get Pb2O2 because you can reduce that down. It should be PbO. And just think, hey, these are the same thing. Their ratio is 1 to 1, so that's what I should get, PbO. All right, so a lot of transition elements have more than one oxidation number, like iron, Fe2 plus, Fe3 plus, copper, Cu plus, has a +1 or +2 charge, and so on. And that, of course, makes some issues here. So here's our kind of common ones. Iron, we talked about, is 2 plus, 3 plus, copper, +1, +2. Tin is often 2 plus and 4 plus, and lead is 2 plus and 4 plus. Those are pretty common transition metals that are in a lot of compounds that we would talk about here. So let's do a couple with that. So, one of the ways that they indicate, hey, which one are we talking about, is that they put a Roman numeral in there. So that says, hey, that's iron 2, which means it's Fe with a 2 plus. Okay. And then chlorine, that's group 7, so we know that's a -1. And so we just can do our little crisscross method, and we get FeCl2. And always check, can we reduce down? No, a 1 and a 2. That's the lowest things we can do. Another way that they might tell you is they just give you the charge. So we say, hey, this is a copper 1 because it's a +1 charge. So we've got copper 1 and sulfur, which is in group 6, so it's a 2 minus. So we would crisscross them, Cu2S. And then zinc, now they didn't tell us, but remember, zinc is one of those that is not a multiple, doesn't have multiple oxidation numbers, so zinc is always 2 plus. Just going to have to start to remember some of that stuff. Br is minus. Okay, crisscross them, Zn, BR2. Unfortunately, there's no simple way to do this other than you just have to remember a lot of stuff. In this chapter, there's a lot of things you're going to have to remember as you're making these formulas. You need to practice this. We'll do a ton of these in class, but you'll have to practice and memorize some of these things. There is no way around that. But that's the end of what we're doing today in section 10.3.